Hello everyone, here is Orillusion. Welcome back to WebGPU basic tutorial. We learned the fundamentals of WebGPU pipeline and the basic configuration method last week. This week we'll learn how to update the data pipeline through JavaScript, which can dynamically change the position and color of the triangle. In the last week demo, in order to demonstrate the whole process of the pipeline, we used a simplified fixed vertex shader to output 3 fixed points, and then used a fixed fragment shader to add triangle as red color. But in the actual application scenario, we certainly can't write the hard-coded shader data like this. We must consider the need to replicate shader and pipeline, which can use JavaScript to cooperate with shader to dynamically change data, and then achieve the purpose of dynamic drawing. So how to change the data dynamically? Let's think about in a normal situation. We actually can have 2 methods. One is the function incoming parameter, and the other one is the function refers to some global external variables. That is similar for the GPU program. We can pass in parameters and also refer in the global variables to control the result of shader. So let's first look into the first method, get the incoming parameters. We've learned in the last week the vertex shader as the entrance to the entire pipeline. If we need to pass parameters, we must pass into the vertex shader first. We call it VertexBuffer slot. We can use setVertexBuffer in render pass. This API will be a GPU buffer inserted into the corresponding pipeline. So in this way, we can pass the parameters into the entry function of the vertex shader. Get information about the vertex data. Then after obtaining these parameters, we can do the different vertex calculation depending on the input parameters and return the coordinates. So for the vertex shader, the final result must contain the required vertex coordinates. Besides, we can also add additional information to the returned result. For example, we can pass the original parameters into the fragment shader. So we can use the entry function of fragment shader to get some parameters and then use them to calculate the colors. So in this way, we can set different vertex information in JavaScript to control the rendering of the entire pipeline to achieve the purpose of dynamically updating data. And as we said, we can also use the form of global variables to do the data management. In WebGPU, we put the management of global variables called resource banding. In GPU program, we can also create multiple buffers and textures. So we can also use the BandGroup to combine different buffers and then use SetBandGroup API to band a group to the corresponding pipeline. And then we can, in the shader, to use the form of addGroup addBinding to get the corresponding buffer information. Unlike Vertex Shader, this combination of group is equivalent to global variables. A group can be in the same pipeline, so the Vertex Shader and Fragment Shader can share the data. But it can also be bound to different pipelines, so the different pipelines can share the data as well. And obviously, this free combination of global groups can make our shader program more flexible and more convenient for us to dynamically update the data in the shader. Today, we'll demonstrate how to use VertexBuffer to update the vertex position of triangle and use BindGroup to update the color of the triangle. We'll directly modify the demo from last week, the basic triangle, to see how to update the data. Okay, initialize WebGPU, we can keep it like this, and we are mainly to do the relevant pipeline settings. Firstly, let's look into how to set up Vertex data. So in the last video, we took the vertex of triangle and all hard-coded in the Vertex Shader. And today, I'd like to put the data into JS to control. And firstly, we need to create a vertex object. And then we put corresponding vertex data in an array. And we need to note here the spatial coordinates of WebGPU. Actually, it is a 3-dimension. But for tutorial, last week we only used plain coordinate of xy, and we fixed the zx coordinate into 0. But today we are going to write this dynamically as well. So we set the 3D data coordinates in the JavaScript and then set z-axis as 0. And second point, we need to know the coordinate system in WebGPU. It's a little bit different between the WebGL coordinate. In the canvas, the x-axis is starting from the left to the right. The range is -1 to 1. And for y-axis is starting from the bottom to the up, and the range is -1 to 1, 2. But the z-axis is a bit hard to imagine here. It extends from the surface of the screen and it's enlarged into from 0 to 1. We'll introduce in detail next time. Let's simply look into the 2-dimension of x and y this week. So 0, 0 corresponding to the center of the screen. Then the 4 corners in the canvas will be -1, 1, -1, -1, 1, -1, and upper right corner will be 1, 1. But here we need to note that GPU shader is a relatively low-level language. It does not have the discrete object structure as JavaScript, and all data must be used the underlying type, which is contiguous memory distribution. So we can't put the ordinary array and object here directly passed to the GPU. We must use the converted form of tabbed array. So here we can directly convert the data array into corresponding tabbed array. We'll explain performance optimization later and especially focus on the use of tabbed array skills. But here, because the coordinates are floating point decimals from -1 to 1, so we usually use the tab float32 array to store the coordinate data. And we also need to create a variable for GPU to store the data. Of course, this variable is a data of JavaScript in CPU. So we need this device create buffer API here to create a variable in GPU. Its parameter setup is simple. Firstly, you need to set a size. And we need to note here, the size is the byte size of buffer, not the length of the array. So the float32 floating point number we would like to save, in fact, every number takes up 4 bytes. So if we would like to save the above 9 numbers, actually we need a 9 multiplied by 4, which is 36 bytes. And that is the size of this buffer. We can also use the vertex byte length, this field, to get the length byte size of float32 array. And the second parameter we need to set here is the purpose of the buffer. We can use the GPU buffer usage interface to get automatic completion. We can see that a GPU buffer can have many various usage. And each usage will have various privilege. Here we would like to have the vertex data, so we choose the vertex option. And then we'll introduce the other options individually. And now we have the variable in GPU, so we can assign it to the vertex buffer. And we also need to write data into it. So how to write data in the JavaScript from CPU to GPU? WebGPU provides 2 methods for us, and today we will introduce the simplest one. And then we can use the device QRead buffer API to copy a tabbed array in JavaScript directly into the GPU buffer. And this is a synchronous operation. So first we need to write down the target GPU buffer, which is the vertex buffer we applied above. And then we need to specify a buffer offset, which is from where in the buffer to start writing. And then we need to write down the tabbed array object in JavaScript, which is the vertex variable. And it means to copy all the contents of the vertex to vertex buffer. But of course, the size of the vertex cannot exceed the vertex buffer size. And note again, offset here is the number of bytes of the corresponding buffer, not the length of the array. So if we like to start from scratch, of course we need to set it as 0. But if we would like to start from the false coordinate, then there is not 3, but 3 multiplied by 4, which is 12 bytes. And of course, we need to start from 0 in our demo. And also, if we would like to give a GPU buffer update its data, we need to set the usage behind the buffer usage to add a GPU buffer usage copy DST. This is used to indicate that this buffer can be used as a target for copy. Otherwise, you can't write data by write buffer. So the data is ready now. And next, in order to let the pipeline to identify the vertex data, we need also add another buffer parameter. It is corresponding to the array. It indicates how many vertex data can be passed into the pipeline. So currently, WebGPU supports only one pipeline and up to 8 vertex data. The number here should correspond to the number of set vertex buffer. And each buffer here must firstly set an array strat, which is the vertex buffer we passed in. And how many data can become a vertex data be passed into the vertex shader. Let's take the example above. So we would like to pass every 3 numbers as one vertex data to the vertex shader. So the number of steps in the array here should be 3 as a slice, which is 12 bytes for one vertex. If we only pass x, y values, then we only have 8 bytes here. Besides, we also need to set up the attribute. This parameter is also an array. So for example, if we would like to put 3 points in a row and add one parameter to pass into the shader, then we should add the shader location as 0, which is to pass the variable into shader at location 0. And offset is also 0. There is another parameter format, indicate the length of our parameter. Because our 3 numbers are all float 32 in a row, so we can choose float 32 multiplied by 3 here, which means we pass every 12 bytes into the vertex buffer. 12 bytes is a vertex and the node is starting from 0. So 3 float 32 numbers will pass into the position in the shader at location 0 as an argument. The parameters is a little bit complicated, but it's fine. Let's take a look into the shader. The above configuration actually corresponds to the following shader. We can get a 1/3 float 32 at the position of location 0 as a vertex data in our shader entry function. If we change the above parameters, for example, we'd like to separate the x, y, and z axis data, then we need to modify the format here. Change it to multiplied by 2. And then the first 2 float 32 values will starting from 0 as an argument. And then we need to add another attribute, which is location 1. And then skip the first 2 float 32 values. And the format is float 32, which is a number. Then we need to pass 2 variables into the shader. One is the location of at location 0, and another one is at location 1, which corresponding to the data for x, y, and z axis. X, y is 1/2 array, and z is a simple float 32 value. So here, WebGPU allows us to pass in parameters in our own way as a fine division. We can also split x, y, z into 3 parameters and pass it in. And we can also split above buffer into 2 buffers, like a XY buffer and a Z buffer. And then we can pass into 2 slots. Then we can have 2 buffers here. The first one is the XY buffer. And the division step is 2. There is no second attribute. The second vertex data is only half Z coordinates, and the number of step is actually float 32, and there is only one attribute. We can insert it into position 1 and then change the format to float 32. Then this pipeline setting corresponding to the vertex shader, and the coordinates of location 0, xy, and location 1, z will be passed in. And in actual scenario, the general vertex shader contains not only xyz coordinates, but also the UV and normal data. We'll talk about it later. And now we can choose to use 3 slots to insert 3 buffers respectively. But you can also choose to mix 3 information into 1 buffer. And then do the internal division through attributes, and then pass into the shader. But in our example, we only need to pass x, y, z. So let's come back. Well, finally, we need to modify the triangle vertex shader we used before. We can pass in this location 0 parameter and then return it back. Then the fixed position array can be deleted. In this way, we can control the data vertex data in JavaScript. And the entire pipeline is set up now. We declare a vertex obj and also a vertex and vertex buffer plus a vertex count. We pack them together with the pipeline and then return it back. We get pipeline and a vertex obj here and pass them into draw. Then we add a vertex obj to the draw and then write any tab for convenient. We just need to call pass encoder set vertex buffer after set pipeline, and then to set the position of the corresponding slot, and then pass in the vertex obj dot vertex buffer. In the end, we just need to draw it. Okay, let's save it and see. There's no error report, and we put the entire vertex data into the JavaScript to management. So we can achieve the purpose of changing the graphics through the data in JavaScript. Let's demonstrate it later. Let's continue to explain how to use the band group to update the color of the graphics. So similarly, we need to declare a JavaScript object to store the color data. It is an array. We can put RGBA for numbers into it, and the interval is from 0 to 1 as the settings of pipeline format. We can convert it into float32 array for storage and convenient for us to write into the GPU buffer. And we also need to create a GPU color buffer through device create buffer. And the size is 4 numbers, so 4 by 4. Of course, we can directly use the color bed length to get the corresponding number of beds directly. As for usage, this time we would like to use a general buffer. There are 2 common buffers in the GPU. One is uniform and the other one is storage. The main difference is that the uniform buffer we only used for some small data, and the maximum is 64 kilobytes, which is read-only in shader and cannot be changed. But storage buffer can be very large. GPU now can support up to 2 gigabytes. And in the shader, this one can be changed. Because in our demo today, the color data we are writing is very small, and we don't really to change this in the shader. So we can only declare this as a uniform buffer, and also add the copy DST label. Okay, we can pass the contents of the color into color buffer through the VSQ wrap buffer. So the data is ready now. And as we just introduced, we need to combine buffers in a form called BandGroup. So we also need to create a group here. Its corresponding API is also very simple. We can call the device create BandGroup. It needs a layout, which corresponding to the layout of the location bind to the pipeline. So for beginners, we can directly use pipeline get BandGroup layout to get the default layout of the pipeline. So we only have one group at the moment, so we can use the layout of position 0. Then of course we need pipeline here, so our group should be created after pipeline. And then we can combine the corresponding buffers and then the corresponding parameters entries. It is an array. Multiple resources can be added here, and each resource must indicate the location of the binding. And we only have one buffer here, so the position is 0. Then specify which resources were used and to introduce the buffer into the color buffer. If there are multiple resources, we can add this into this form in turn. And then one group in the current WebGPU can support binding up to 8 resources. And now a simple bind group is completed. Now we can package our color data as color obj and put the color and the color buffer and group together into this object and then return it out. So similarly, we can get the color obj here and then pass this into draw and then add a new color obj in the draw and then also set any for the type. Like set vertex buffer, we can use pass encoder SetBandGroup to bind the pipeline into the group. And we need to pay attention here, the position should be consistent with the layout set in the group. Because we specify that the pipeline corresponds to the layout of 0, so we can only bind group to 0, and then pass the color obj.group in. And after setting up, we can modify the fragment shader we used before. Can use add group 0, add group 0, binding 0 to get a uniform buffer, which is 1x4 array, and content is a float 32. Then we can use the color variable from here and then return the color, just like the vertex data. So now we give the control of the color into JavaScript. We can modify the data in JavaScript. So let's take a look how to use the JavaScript to do the UI interaction to dynamically change the color and position. Well, the code is simple. So we added two UI, and one is to change the color, and one is for the range input. Let's look into the range input firstly. We add an input listener to it, and then we can use the callback function in the event to get input value. And we can see that the range will vary from minus 0.5 to 0.5 added to our x-axis coordinates. Then we use write buffer to write the new data into the Vertex Shader and then draw again. And it will override the previous graphics. Because Vertex buffer data has changed, so the corresponding Vertex Shader input value is also changed. And the output value of the Vertex Shader also changed. Then the position of the final graph will be translated according to the data we input. Let's take a look. Okay, the color input is the same. We get the first from the input change. And here we are using the hexadecimal color data. When the color changes, we get the hexadecimal value, and then we need to do some simple calculation to transfer the hexadecimal string into a corresponding decimal value from 0 to 255. And to conform the format that we need, we also need to normalize the value from 0 to 255 to 0 to 1. And finally, let's update the data in color obj and then update the color obj color itself. And then put the color obj color into the color obj color buffer. And then it's the same, we draw again. So the final effect is when we change the color of the graph will change correspondingly. And please practice after class the specific process of these two callbacks and see how to change the vertex data to make the graph change, like rotate or zoom in. In the next video, we'll learn how to do the basic drawing for the 3D graphics and then understand how to use the transform matrix to do the translation, rotation, and the scaling in the vertex coordinates. And then finally, we can make a 3D cube that rotates like this. Okay, that's all, and welcome to subscribe our channel. I'll see you next time.